next lesson, which is 1.1b. It's called the tangent problem. And the tangent problem is fundamental to the first branch of calculus that we're studying, which is called differential calculus. Yesterday I went through differential calculus, which is concerned with finding slopes of functions. And I talked about integral calculus, which is consumed with trying to determine areas beneath functions. But we're not going to get into integral calculus until, well, I would normally say May, but I can't wrap my head around this whole schedule until the last unit. So we're going to look at the tangent problem. I will tell you right now, everybody, that at the end of this lesson, you should be able to figure out how to do assignment 1A, but I do not want you doing 1A using what we learn in this lesson, okay? I will let you know when you have the algebra skills that will allow you to solve question 1A, and I believe it's tomorrow. It's Friday, okay? So we're going to understand how the slope of a secant line can be used to determine the slope of a tangent line. So to begin with, we have two words here, secant and tangent, which, as far as we're concerned, have nothing to do with trigonometry in this unit, okay? A tangent line has got nothing to do with opposite and adjacent or y and x or anything like that. And a secant line has nothing to do with the trigonometric ratio secant of theta. You'll learn what a secant line is and what a tangent line is and how they're connected. And then we're going to be using this connection between the two to determine the slope of what's called a tangent line. And to give you an idea of why we have to do it this way, why we're going to do what we're going to do, it's impossible for you to find the slope of a tangent line directly. So you find the slope of a secant line instead, and you figure out how it can lead you to the slope of the tangent line. So to begin with, what does the word tangent mean in this context? If I gave you a circle and said, sketch a line that's tangent to that circle, and you sketched that, that's tangent. And if you ask people to explain what the definition of a tangent line is, some people will say, wrongly, a tangent line touches the curve in one place. But it's a lot more complicated than that, because if you take a look at these two graphs, the graph on the left has a function that's curvy, and it has a tangent line. And that straight line is, in fact, tangent to that curve at x equals 2. I want to really make sure you understand what those words are saying. This line here is tangent to this curve at x equals 2. Intuitively, we can see it's tangent. It just kind of touches it at that point. But you will notice that the line, the tangent line, actually goes through the curve in more than one place, doesn't it? It crosses over here somewhere around negative 4.2. Whereas the line on the right clearly is not tangent, even though it only touches the curve in one place. So it's a very complicated thing trying to decide what tangent means in this context. So the straight line is tangent to the function on the left diagram, but it's not tangent to the function on the right. Now, what is important is that the slope of a tangent line at a value of x on the function is the same as the slope of the function at that point. That may seem obvious until you really think about what I'm saying. I'm telling you, this is sometimes called the instantaneous slope, by the way, at a particular value of x that we call a. What I'm telling you is that if the slope of that straight line that you're looking at on your screen right now was 6/7, if it was 6/7, then the slope of the curve at that point is 6/7. And prior to this lesson and prior to calculus, you've always kind of talked about slopes of straight lines, and you never really talk about curves. Although we, in physics, we kind of do a little bit of that. So make sure you understand the distinction between talking about the slope of the tangent and the slope of the function. The slope of the tangent line, I don't know if it's 6/7, I just kind of pulled that out of thin air. But if the slope of that tangent line is 6/7, the slope of that line is 6/7 everywhere. But the slope of the function is 6/7 at that point. If you were to go and look at a tangent line at 2.1, you would discover the slope of that tangent line would be different, which means the slope of the function would be different. It would be steeper. Whatever the slope of the tangent line is, that is the slope of the function, even though the function is not a straight line. One more kick at the cat, horrible expression here. The slope of the tangent line is the slope of the function at that point, which is why we call it the instantaneous slope. If you go a little bit to the left, the slope will be different. If you go a little bit to the right, the slope will be different. So we're going to use a ruler, and we're going to get some practice in understanding what a tangent line looks like. You've got a graph that shows the cooling of a pot of spaghetti once the burner is turned off. You'll notice I highlighted a number there because I have a typo in my printed version of your handout. It goes 0, and then it has 20, 20. It should go 20, 40. So we want to determine the slope of the tangent line. And there's a lot of words here that I'm about to bring forth to you. But I need you to understand that the slope of the tangent line to this graph at t equals 10 minutes is going to be the rate of change of the temperature with respect to time at 10 minutes. In other words, it's going to have units of degrees Celsius per minute, whatever number we get. That's what we mean by rate of change. You analyze the units. The vertical units are degrees Celsius. The horizontal are minutes. So what we want to do is draw the tangent line. You want to take a ruler and draw the tangent line. Now, I can't put a ruler on my smartboard to show you this, but I'm going to plot the point first. It was at 20 minutes, is that right? 10. So I'm just going to plot a point, which is right here. I'm going to get out of here so I can use my lines. Don't draw anything just yet. Give some thought to what I'm saying. I hope it's clear to you that that is not tangent to the curve at 10 minutes. There's no way. It's not steep enough. And on the other hand, that is not good. We understand that since the curve is kind of concave from a certain perspective, that the tangent line has to have both ends on the same side of the curve. But then it becomes tricky because if you draw this, whoops, if you draw this, and I draw this, that's a significantly different slope. So how on earth do you decide how to put your ruler down? Well, I'm not going to bring up a ruler here. I could, but it's really not going to be helpful in my explanation. What I'm going to show you is kind of the way that I've come up with over the years to explain it and how to do it with a ruler. You want to draw a tangent line in such a way, I got to put this point back on here. Let me draw one in first, and then I will explain to you what my rule is. You want to draw it in such a way so that there's just as much air in between the curve and the tangent line on both sides of the point. What I mean is when I look at this and I look in here, I see more air, more space between the curve and the line on that side of the point than I do the same distance away on the other side of the point. It's the tangent line I've drawn is too close to the curve here. I want to have the same amount of air. It's asking for trouble. My computer is going to freeze probably. This air here, you can see a fairly significant sliver, and then look where the sliver is here. You want to rock your ruler back and forth. You want to put your pencil point down on that point, push your ruler against that point, and rock the ruler around until you see just as much air on both sides. I hope. Oh, worked okay. So even though this line is not touching the point right now, if you look at the space, it's pretty symmetrical, isn't it? So if I just slide this against here, I would say that that's pretty good. Could maybe move it a bit more. So that is the line. So how are we going to use that to find the slope? We're just going to use rise over run. You're going to pick 2 points, and I didn't do this intentionally, but this point is pretty readable, and I would say this point I'm going to have to estimate. You are going to have to read those points as accurately as you can. Clearly, I shouldn't say clearly, because if everything was clear, I wouldn't need to be here. You don't count squares. You look at the numbers on the axis. So while you're working on that, I'm going to continue to talk and do my work here. My rise is from 10, and you certainly don't need to draw all of this, to what I would say is 88. I would say that's 88 on mine. Okay. So for my first line, my slope will be 88 minus 10. These are degrees Celsius over, what will my run be? My run goes from 0 to 30. I'm just using rise over run. I could go y2 minus y1 over x2 minus x1. It doesn't really matter. So this would be 30 minus 0. This is minutes, which is 78 over 30. We like to not use decimals most of the time. But since we're kind of eyeballing things here, and the number we're getting is supposed to represent degrees Celsius per minute, I think it's reasonable to calculate it in minutes. Yeah. Thank you very much. Yes, they would. Definitely. Taking a note from what I said earlier, which is that you have to subtract in the same order, and I didn't follow my rule. So you end up with negative 30, which, by the way, makes sense because the line goes down, right? That's 39 over 15. I don't know what that is. That's 2.6 something, or I don't know. It works out to negative 2.6. So what is the slope of the tangent line? Negative 2.6 degrees Celsius per minute. I would be really shocked if all of you got negative 2.6. Like picking your points. Unless you pick the same points, you're likely to get a slightly different answer. So what does that mean? That means at that instant in time, and I want to talk about this is an instantaneous rate of change, but there's something we need to understand. At that instant in time, the temperature is decreasing at 2.6 degrees Celsius per minute. And some people are bothered by that statement because a minute is not an instant in time, right? But if you're driving down the highway, you're at some lights and then you pick up speed to enter the highway, and you are speeding up and you look at your speedometer and it happens to say at an instant 85 kilometers per hour. Does that mean you've been traveling for an hour? Well, no, it just means that that's your speed at that point. So don't be bothered by that minute thing. We also want to find it at 50 minutes. So you're going to draw another tangent line here. This time you're going to put it at 50 minutes. I'm going to give you a minute here while I work it out as well, and we can compare our answers. And by the way, this is not how we're going to find slopes of tangents in this course. This is just warming up. Oh, let's go green again, this point, and let's go. By the way, not that it really matters, but you should be picking points that are fairly far apart. I don't think you want to pick 2 points that are really, really close together. Normally, by the way, it's your rise that's negative. It doesn't have to be, but you need to understand this is a negative slope. What are we looking at? 100. And it goes down. What is that? 37 to 8, 10, 20, 29. $37 minus 29. 37 minus 9 is no 30. Oh, minus 8. I said that was 8. So 37 minus 8. There we go. I want to make sure. You get negative 0.29 is what I get. You get in the neighborhood of that. That makes sense. If you've ever done any cooking, you understand that when something is very hot, that's when it loses a lot of heat in a very short period of time. You come back 10 minutes later, it's, don't touch it necessarily because it could still burn you, but it's cooled down a lot. But then you find in the last part, it's like an hour goes by and it's not changing temperature very much. Any questions with example 1? All right, example 2, I think, encapsulates what it is we're doing in this course. So now we have a function. The function is f of x equals x squared, and I've plotted it on a graph for you from 0 to about 3. And we want to determine the equation of the tangent line to that function. So how do you determine the equation of a line? I mean, you should know a tangent line is a straight line. And a straight line has an equation that's found using the point slope formula, right? That's what we learned in the first lesson today, or we reviewed it. So what are the things that you need to know? Well, you need to know the coordinates of a point on the tangent line. And by the way, the point is there. You can see it. Because it's tangent at 3/4. Here's another thing that I think is obvious to many people, but it bears repeating. It's not obvious to everybody. If the line is tangent to the curve at x equals 3/4, then that point on the curve where x equals 3/4 is also a point on the tangent line. There's a difference between saying the point on the curve and the point on the line, but if it's tangent to that point, they're the same point. So I guess what we have to do first is draw the tangent line, just so we have an idea of what it is we're looking at. So take your ruler and draw a tangent line. You don't have to actually draw this if you don't want to, because we're not going to find the slope using it. We're going to find it in a different way. But I think if you have it drawn on paper, it'll help you visualize things. Doesn't have to be perfect. So we want to determine the equation of that line. Again, I want to go through this slowly. These two things at the bottom of this screen that you're looking at are things that we need to know. The coordinates of a point on the line and the slope of the line. Well, the coordinates of the point are going to be easy because we know the equation of the function is f of x equals x squared. And the x coordinate of the point is given to us, right? This is what this question is asking us. What's the y coordinate when x is 3/4? Well, get used to talking about points this way. We'll figure out what y is equal to in a second. But if x is 3/4, then the y coordinate is f of 3/4. And f of 3/4 is going to be 9/16. Why? How come? Because f is x squared. F means to square x. That's what the function is in this example. So when you square 3/4, f of x is x squared. So f of 3/4 is 3/4 squared. You square 3/4, you square 3 and get 9, you square 4 and get 16. So we can label that point on the graph. Now I've put in 3/4 comma 9/16 with the letter P. You could label it just as P if you like. If you're going to keep up and draw everything that I am going to put up here, it's going to get very busy. So you might want to hold back on writing stuff until you know what it's going to look like. I want to just tell you that point P is what I'm going to call a fixed point in this question. It's not going to move. No matter what we do, this is the point we care about. Just for kicks, let's estimate the slope. Let's find the slope of your line that you drew. This is not how we're going to answer the question, but let's do that to see, kind of what we get or what we should get. I wouldn't mess up your graph with this. I would do that someplace else where you have space. I would have 4 minus 0 over, let's see, this is 3.25. Oh man, I don't know, 3.15. That's about 3/5 of 25. Yeah, 3.15 minus, that's about 0.25 plus another 0.15, 0.4. It's not going to be pretty here. It's not like it's going to work out to something precise. $1.45 is what I get, roughly. What'd you get, Dan? 1.33, Cambry? 1.48, Julian? 1.44, and I won't ask the rest of you because you're too far away for me to hear you. Or in around 1.4, 1.5, around there. So this will just give us an idea of the reasonableness of our answer. When we get an answer and I convince you that the answer we get is right, we'll be able to say, see, it's really close to what we thought it would be. So now what we are going to do is I've got a table there with 6 other points. I'm going to call these points Q, Q1, Q2, Q3, Q4, Q5, Q6. And these points are what I'm going to call mobile points. They're points on the move. And if you take a look at the x-coordinate of Q1, it's 3. The x-coordinate of Q2 is 2.5, then 2, 1.5, 1.8. And what's crucial to your understanding here is these x-coordinates of this point that's on the move are getting closer to the x-coordinate of P, which is 0.75. That's really important. So the first thing we want to do is we want to calculate each y-coordinate for all of these. So I'll give you a minute to do so. These points are all points on the curve. They're not on the tangent line, they're on the curve. Because some of these numbers are going to get awkward in decimal form, I've got my answers up here in fractional form, I think. Oh, no, I lied. I got them in decimal form. But you're just squaring all of these, right? So now we want to plot those points. Well, the nice thing about plotting these points is you really don't care what the y-coordinate is just yet. If you want to plot the point where x equals 3, you just go over to x equals 3 and you plot that point on the curve. So you're going to have these points. And believe me, what we're doing and what we're about to do is not how you would do this problem. A week from now, you're going to look at everything we've done over the today, tomorrow, and Friday and roll your eyes and go, oh my God, that was a lot of work. And it doesn't need to be, but we have to start here. So I've labeled all of these points. Well, I haven't labeled them. I've plotted all of these points. The line that I have drawn there, by the way, is the tangent line. Okay. So now what? Well, a line connecting point P on the curve, where the line of tangency, which is what we're after, is located, a line connecting that point and another point on the curve is called a secant line. So this is a secant line. This line that goes through P and Q1 is a secant line. It's not a tangent line, okay? What you are asked to do is find the slope of each of these 6 secant lines. Now let me explain what that means. We know, if I got it here, we know, I'll do the slope of the secant between P and Q1 together with you, okay? Well, we know that P has coordinates of this, and we know that Q1 has coordinates of this, so the slope would be 9 minus 9/16 over 3 minus 3/4. Now, before we calculate it, we can, well, no, let's calculate. We've come this far. Let's calculate this thing. I'm taking y minus y over x minus x, so I'm just applying what we've already done with slope calculations. So 9 minus 9/16 divided by, in brackets, 3 minus 3/4 gives me a slope of 3.75. Now, before you run away with this and start doing all the calculations, just maybe put your pencils down, stop what you're doing, and just watch and listen to what I'm about to show you. This is going to be a very tedious process, fraught with lots of room for error, because you got 5 more to go. I want you to notice, and you're not writing this down, I want you to notice that if you wanted to find the slope of the secant line PQ, it would be this. Oops. Come on. Don't calculate it. I just want you to look at that and see if that makes sense, what I've done. Okay. So what's changed in going from the slope of PQ1 to PQ2 is that this number went from 9 to 6.25. This went from 3. Just a second. Did I write something down wrong here? Let me back up. 9 minus 9/16. 6.25 minus 9/16 over, I wrote down the wrong number, 2.5. Does that make sense? Okay. So in the next calculation, you're going to change the 6.25 to 4 and the 2.25 to 2, right? Now I want to go a little further and tell you that what you have actually up here is the x coordinate of q minus 3/4 over the y coordinate of q minus 9/16. But the y coordinate of q is x squared. I'm going to show this to you visually on a graph, that I don't care where q is. It will have coordinates of x comma x squared, won't it? Whatever the x coordinate of q is, you square it to get the y coordinate. Well, that means that your secant slope is always going to be x squared minus 9/16 over x minus 3/4. I realize, and I know from experience, that's going to confuse some of you. And for that reason, if you want to find these secant slopes, you can ignore everything I said here and just go ahead and calculate all of them in the same way. But in a very general sense, if Q is at this and P is at this, then the slope of PQ is x squared minus 9/16 over x minus 3/4. So why don't we use that idea with our calculator? Why don't we put in, for y, I'll be very careful here, this y that I'm putting in is a way to calculate the slope of a secant. It's x squared minus 9/16 over x minus 3/4. I'm putting this in for y in my calculator, but it's not a y coordinate, it's the slope of a secant. I'm going to be using my tables to calculate all of these. So my slope of the secant is going to be equal to x squared minus 9/16. If you haven't been in my math class for a while, that's just how I enter x squared. Don't ask why, I don't know. Divided by x minus 3/4. And this means, everybody, that if, I'm going to try this from another angle, that if I put x equals 3 into that expression, I will get the slope of the secant from P to the point where Q is at x equals 3. And what that means is I can set up my table, second window, and change it to ask for the independent, which is x, go to my table, and I can enter 3 and 2.5 and 2. And I can calculate the slope very quickly and without risk of error. Regardless of how you want to do it, I would like you to find the slopes of the 6 secant lines, but I would also like you to note that if you choose not to do this, there will come a time where you have to understand this. It's going to happen day after tomorrow. And when you do understand this, then there will be a way to do assignment 1A properly. Once again, from the top, since Q bounces around from place to place, it has no defined ordered pair. Wherever it is, that is the pair of numbers that you would use to find the slope of the secant. P, on the other hand, is at 3/4, 9/16. So if you take y minus y over x minus x, you get that. Okay. How many of you have done the 6 secant lines? Just compare them. Yes? Okay. So, what does this mean? And this is a visual thing that I'm going to show you here. So you need to follow along up here. It means that the slope of secant line PQ1 is 3.75, and clearly the slope of that secant line is not the slope of the tangent, right? These two lines have different slopes. If we calculate the slope of secant line PQ2, we get 3.25. Now, is the slope of that secant line PQ2, which is drawn in black, is that the same as the slope of the tangent line which we're after? No. But is it closer to being the slope of the tangent line that we're after than the secant slope for PQ1? Absolutely, it's closer. And I hope you understand that as we move Q closer to P, the slope of the secant line, although never being equal to the slope of the tangent, does get closer to the slope of the tangent. So these two lines are clearly of different slope, but they're closer in slope value than these two lines. And if we go to Q4, they're getting really close. If you go to Q5, look how close point P and Q5 are. They're very, very close, but the lines are not parallel, obviously. They never will be. They never will be. No matter how close Q moves to P, you will never get a parallel line, but it will always get closer. And if you take a look at this one, look at those 2 points. Look at these 2 points, P and the red dot right next to it. They are so close to each other, but the lines are not the same lines. Are you with me on this so far? So what if we went really close, which I can't draw? What if I drew a secant line from point P to Q, where the x-coordinate of Q is 0.76? The x-coordinate of P is 0.75, right? So imagine me drawing a dot at 0.76 and drawing a secant line in there. It would probably be pretty close to the slope of the tangent. And we could certainly not draw it, but I can certainly go to my calculator and put in 0.76, which is really, really close to 0.75. I don't want it to be lost on you. When I put in 0.76, I'm choosing Q to be incredibly close to P. And the slope of the secant then would be incredibly close to the slope of the tangent. And I can push it. I can go 0.751. That's really, really close to 0.75, isn't it? And we could go 0.7501. And we see a pattern emerging here that the slope of the secant, don't forget this says y, but y represents the slope of the secant, is getting really, really close to 1.5. Okay, so we're going to put that all together now. The slope of any of the PQ secant lines will never be equal to the slope of the tangent line, ever. It's impossible. But what's the relationship between the slope of PQ and the slope of the tangent line as Q approaches P? We write it this way. As Q approaches P, the slope of PQ, which is a secant line, approaches the slope of P, which is the tangent line. This is going to lead us tomorrow to what are called limits in calculus. I hope that what we've written there, that notation, makes sense to you. I want to add one more thing here. We could say that as x approaches 3/4 in this question, the slope of the secant approaches the slope of the tangent. There's lots of ways to communicate it. Whether I say slope of PQ or slope of secant doesn't matter. This is the fundamental idea behind finding the slope of a tangent, at least for now, and even later. Wait a minute. If I just keep putting in values for x of point Q closer and closer to the x coordinate of P to get a secant that's closer and closer to the slope of the tangent, why don't I just put in 0.75 for the x coordinate? Well, because I can't. Because then your slope calculation would be 0.75 squared minus 0.75 squared over 0.75 minus 0.75. You can't do it, right? I'm going to come back to that idea. I already wrote that out. Use this idea developed to find the slope of the tangent line. Well, we suspect it's 1.5, don't we? And I will tell you it is 1.5. And if you go back and you take a look at your estimates, 1.33, 1.48, 1.45, 1. Whatever, I can't remember, they were all close to 1.5. So the slope of the tangent is 1.5, which is 3/2. Now, I could have told you it was 3/2. I really could have. And you will be able to on Tuesday of next week by simply looking at this function. You'll be able to look at that function and go, oh yeah, the slope at 3/4 is 3/2. There's a way to do it, okay? What's the equation of the tangent line? So we've gone on a pretty big journey here. But remember, to determine the equation of a line, you need to know two things: an ordered pair and the slope. And now we know them both. We use y minus y1 equals slope times x minus x1. We load in all of these things. We'll have y minus 9/16 equals the slope times x minus 3/4. This is a weird case algebraically. We're going to try to get rid of as many of those fractions as possible, but we may get rid of them and then they may come back. All right, so just be aware of that. I'm going to multiply both sides of this equation by 16. The reason why I say they may come back is this is going to get rid of this 16 and it's going to get rid of this 2. It's not going to get rid of the 4 inside of the brackets, but I suspect it will go away once we multiply it through. So I get 16y minus 9 equals 16 times 3 over 2. Well, 16 over 2 is 8. 8 times 3 is 24. And my suspicion was right. When we multiply that 24 through, we will get rid of that denominator of a 4. How's my arithmetic on that? 24 times 3/4 is 18. 24 over 4 is 6 times 3 is 18. So we get 24x minus 16y. Negative 18 plus 9 is minus 9, which is equal to then 0. So is my arithmetic in that last step okay? Okay. So now I want to discuss some things with you. We're done the lesson, right? But I want to discuss some things with you. One of them is that if we go to y equals and we clear it out and we put in the function, I used to not show students this until the course was almost over, but you have to be able to do the work on paper anyway, and this is only a way to check your work. And I graph this. Let's go zoom standard, which is zoom 6. If I want to determine the slope of the tangent to this curve at a particular point, my calculator can do it for me. Okay, I go to the calculate menu, and I'll tell you right now, if this is all you do, if you think you can do this and pass the course, you're mistaken. Okay, I don't mean to be that blunt, but it's not a way to learn math. It's a way to check your math. And you choose number 6 under the calculate menu. That's pronounced dy dx. It's not dy over dx, it's pronounced dy dx. And you choose that, and then it just kind of hangs there. Enter the x coordinate of the point of interest, and you get the slope of the tangent. If you really want it to be fancy, you can go to your draw menu, which I don't know that you've ever used. It's second program. And you can draw the tangent line at 0.75, and it draws it, and it gives you the equation of the tangent line. It gives it to you in the form y equals, but it's there. Now there's one other thing I wanted to show you. And although after seeing this, you might think you have what's necessary to do assignment 1A, I'm going to tell you you can't, okay? Because you don't know the proper terminology and notation. We said the slope of the secant line is equal to x squared minus 9/16 over x minus 3/4. And we're going to talk a lot about this Friday. We're going to get more practice with coming up with this general expression for the secant. And we wanted the slope of the tangent at x equals 3/4, but I can't put 3/4 in there, right? I can't. It's impossible. Maybe we can open up that math toolkit and do something to that expression so that it will allow us to take in 3/4. Well, I would multiply the top and the bottom of this expression by 16. Let's see what we get for the slope of the secant. We get 16x squared minus 9 over 16x minus 18, I believe. You want to check my math there on that? The top is a difference of squares. The bottom has a common factor of that should be a 12, shouldn't it? Not 18, 12. The bottom has a common factor of 4. And what's about to happen, everybody, and I am dead serious. I've taught this course 15, 20 times. I am always amazed that it happens. No matter what point on the function you pick, you could have picked 3/4, 9/16. You could have picked 0.1, 0.01. It's always possible to factor it so that the part that is preventing you from putting 3/4 in, or whatever the x coordinate is, that cancels. I am truly baffled. It doesn't matter what the point is, you're going to get something that's factorable. If you picked 0.785, you'd get something that's factorable somehow. So we're left with this expression. Now, are we allowed to put 0.75 in? Well, technically no, because it's still a non-permissible value, but go ahead and do it anyway. Put 0.75 in and see what you get. Three over 2. So if, and I'm going to go through a different example with you in a second here, if you understand how to build a general formula for the slope of the secant, and you understand that if you can eliminate the part that's preventing you from putting in the x coordinate at P, then you don't need to mess around with calculating all these separate slopes and finding out what the slope is approaching. Okay. If I were to go to Aaron's assignment and he wanted to determine the slope of the tangent to that function at x equals 11, then the idea is, I don't know what the function looks like, but here's P and it's at 11, comma, we're going to do a little bit of Aaron's work here for him. Calculate the y coordinate on this function when x is 11. It's going to be a bizarre number. Well, not bizarre, but I want to say negative 117 thirds. Okay. So here's a point Q. Is Q fixed? No. Q roams all over the place. The only condition is Q cannot be on top of P. Since Q moves all over the place, the coordinates will be this. Because, yeah, Oh, it reduces down. Oh, thank you. I was wondering why you weren't agreeing when I said negative 1/17. So 117 over 3 is negative 39. Okay. Um, that's going to happen a lot in this course. We don't rely necessarily on the calculator, so you do something like that and you don't realize it. So negative 39. Oh, Aaron's job just got a little bit easier. So point Q can be anywhere. Can be anywhere, except the x-coordinate cannot be 11. And that means that this is the slope of the secant line. I don't care what the graph looks like. That's the slope of the secant line. Here's the tangent line. So the slope of the secant line is equal to y minus y1 over x minus x1. And in that expression that I've come up with the leaning 8, in that expression, if x gets closer to 11, that expression gets closer to the slope of the tangent. But you still, I don't want you doing assignment 1A yet, but I'm telling you, this is kind of the approach we're going to take. We're going to use something called a limit instead, though. And I guess maybe I will leave it there. You're going to be doing 7, 8, 9, and 10. And if you look at what 7, 8, 9, and 10 ask you to do, they ask you to find the equation of the tangent line to the function at the point. I don't care if you take this point and this q value and calculate the slope of the secant and then repeat it with this q value, this q value, this. I don't care if you do that. I don't care if you do what I suggested to do back here, which is to build this formula for the secant and then break it down somehow. What I care about is you do not just plug the function into your calculator and find the slope of the tangent with your calculator. You have to find the slope of the tangent to determine the equation of the tangent using the idea that we learned. As q gets closer to p, the slope of pq gets closer to the slope of the tangent. So 7, 8, 9, and 10. This is pretty weighty stuff, pretty heavy stuff. You may need to really think about it. As soon as you have a question with any of them, please ask.